So now let's welcome our research presenters for a round of GNSI Research Quick Shots. Joining us today are, so I'm just going to go one by one, and as I introduce you, please go ahead and take 5 minutes to present us your research. Dr. Paul Hungler is an associate professor in the Department of Chemical Engineering and Ingenuity Labs at Queen's University, Canada. Dr. Hungler's research is focused in using machine learning to develop intelligent, dynamically adaptive simulations to enhance education and training. And he is currently on sabbatical at the University of South Florida. Please, Paul.
Thank you. Thank you very much. I've thoroughly enjoyed my time here in Tampa, being on sabbatical from up north, enjoying the sun. So thank you. My research...
Sorry, that's mine.
Go in reverse. That's me. So my research, I received a grant from the IDEAS. It's the Improving Defense and Excellence in Security, so kind of a Canadian DARPA version of funding. And it was really focused on developing intelligent simulation. So the idea to try and deliver individual training, so personalized training to everybody in the training system, and this was focused on medical trauma simulation. If you want to go to the next slide. So the goal was individual training. So what we did was we brought in trauma team leads into medical trauma simulations, and because it was defense funded, it was a gunshot wound and blunt force trauma. And what we did is we used some previous training data that we had from driver simulation and other domains, as well as MAT2B from NASA. We put that information in, and what we're doing is bringing the physicians into the trauma simulation. We're collecting a bunch of data during the simulation, and then using that data to take the simulation that we've created. And as you can see there, the simulation, the physician goes in, one of the physicians, there's a full trauma team there, but one of the physicians has Oculus, not the Oculus, no, they have the HoloLens in this augmented reality, but we've created an overlay over top of the mannequin, so that we're able to change the actual difficulty of the simulation and the temporal speed that we deliver to the physician. And during that time, we're calculating a bunch of different sensors. So next slide. Perfect. So while the physician is in there, we're collecting a ton of different data, ECG, EEG, as much stuff as we could put on the physician's head as possible with the HoloLens as possible. And then we have FNIRS as well as eye tracking. So we're collecting all that data in real time. We created a machine learning pipeline where we took all that data, and we did it in different trials. So we didn't put it all together. We're in that process of doing it right now, different modalities to get through, but multimodal data coming through, using that in real time to adjust the simulation. So if you go to the next slide. Right, so basically this is the kind of pipeline. It's that feedback loop. So we got all this. In this case, the initial one was just galvanic skin response, so sweating and that, and ECG, so heart rate monitors, going in, taking that, putting it through a convolutional neural network, bringing it back, and adapting the simulation in real time. We got some, and what we're really trying to do is we're looking at cognitive load and expertise. Those are the two factors we're trying to classify. We're taking expertise as whether they're a medical student or a attending physician, going from there, and then for cognitive load, we're kind of getting real-time identification from the actual participants in there, and retroactive, them looking at first-person video after the thing to kind of do labeling for our data and put it through there. So we did that as our training data, then we brought it in, had a number of different testing and validation scenarios where we brought them in, and we're trying to use this simulation to change it in real time based on our classification of cognitive load as well as their classification of expertise. And so really the goal in this whole thing is to get that personalized individual training at the end to be able to increase and improve learning outcomes. In the military, and I was Royal Canadian Air Force 20 years before I came over to academia, everybody's in training for so long, and we wanted to be able to use augmented reality and some of these new techniques in simulation to provide individual and personalized training. So, because the poster outside can talk to you some more about the new classifiers and machine learning algorithms that we're using with FNIRS and some of the things to get better estimations and higher order estimations for cognitive load through my grad students and stuff. So thank you very much.
Paul, thank you very much. And as Paul said, the posters are outside, so you'll get plenty of chance for the questions and answers to find out any other more information you would like for the researchers. Next, we have Nicolas Bustos. He joined the USF program, PhD program of Industrial and Management Systems Engineering in 2021. His research areas of interest are optimizing in the energy market and computer vision. Nicolas?
Thank you. Thank you for having me here. I'll present to you now my current research. We named that FT-CycleGAN, a novelty frequency-based loss function for visual and IR image translation. So for that, let me introduce first what is a Fourier transform. It's a well-known mathematical decomposition that is using computer vision for decomposing an image into its basic frequency domain or components. So imagine looking at a picture as if you were analyzing a musical by its pitch, right? So that's the frequency from the music. Is it useful for computer vision? Of course. Feature detection relies on that as well. We can isolate many of those frequencies in images to identify some features and use them in CNN networks. We use that for image filtering as well, as high and low frequency spectrums. They convey different type of information. So, for example, as you can see in the right side image, we're isolating the high frequency of the image, and we have a more smooth, blurred image. So that's usually used for noise reduction, which is the next point in the bullet points, because we can eliminate unwanted frequencies. And we can use compression. We can use Fourier transform for compressing images, so we only save the important frequencies, and then for pattern recognition, which works along with feature detection. If you go to the next slide. So in our work, we're using CycleGAN, which is a well-known generative adversarial network that works with two generators and two discriminators to create realistic images of a target domain. But for this type of network, we put two generators and two discriminators in a cycle framework. In our current work, we're using as well two more discriminators for the Fourier transform domain or the frequency domain. So the generators not only have to generate a realistic image to fool the spatial domain, also has to fool the discriminators in the frequency domain. We use that for image augmentation, which is increasing the data information and train sets. We can also use that for fusion techniques. Because the RGB, for example, in our case, we're using RGB and thermal images. Both together can leverage the performance of models as object detection, for example, models. If you go to the next slide. So you can see some results here. We have an RGB image, and we have a comparison using CycleGAN, which comes from the paper as itself, and then FT-CycleGAN, which is adding the Fourier transform component to the cycle loss, and then FT-CycleGAN 2, which is using the two extra discriminators in the network. So that's pretty complex for the translation, but you can see in the last column a real thermal image that is showing underneath the car that has a higher temperature. Usually is where the pipes go. So all the metal is obviously higher, has a higher temperature. And you can see the same features in the FT-CycleGAN 2 column. As opposed to CycleGAN itself and FT-CycleGAN, that's showing just a different colorization of the objects in the pictures. So if you want to see more details, I'll be outside in my poster and we can discuss more about this. That's it. Thank you.
Thank you very much, Nicolas. Next, we have with us Dauen Lee. He is a PhD student in the Department of Applied AI at Soong Kwan University and a visiting scholar in computer science and engineering at USF.
Nice to meet you. I'm Dauen Lee from South Korea, and I'm currently visiting researcher, CS department. And my research is about aphasia type detection, and this research is previously published at well-known NLP conference last year. It's called EMNLP, and so it's my honor to introduce my research paper. Can you go next slide, please? Okay. Aphasia is a language disorder caused by brain structure damage and affecting speech functions. So depending on symptoms like severity or fluency comprehension, aphasia can be classified into 8 types. So accurate identification of aphasia type is essential for effective treatment and rehabilitation. And since people with aphasia often rely on nonverbal communication technique like gestures for supporting their difficulties in word retrieval, we propose utilizing both speech and gesture information is crucial in classifying aphasia type detection. Next slide, please. So based on this, to analyze the correlation between speech and gesture modalities, we developed a novel deep learning models, and we use multimodal graph neural network to capture the relationship between speech and gesture, and then here, I think it's better to explain about my model after next poster session. And here we use aphasia open database, and we employ automatic speech recognition system for effective data processing. Can you go next slide, please? Okay. And the proposed model achieves state-of-art result for aphasia type detection, and it highlights the effectiveness of integrating gesture information with speech pattern. And here we found gesture features significantly outperform acoustic features in aphasia type detection, and it underscored the importance of nonverbal communication cues for aphasia, people with aphasia. So here we believe our research can provide clinicians with a deeper understanding of aphasia and to help facilitating for more accurate diagnosis and timely intervention. So here, if you are interested in our study, you can visit our GitHub site, and you can see more detail about our research. Thank you.
Thank you, Dauen. Next, we're so happy to have with us Mehrsa Mashhadi. She is pursuing her PhD in Industrial and Management Systems Engineering Department at USF. Her research interests lie in the field of computer vision and machine learning.
Hello, everyone. My name is Mehrsa. I'm so happy to be here. Thank you for having me. So our research is to analyze the impact of using synthetic data for object detection. So as you know, in the literature, we have different modalities, and it has been shown that using fusion algorithms can improve the performance of object detection models. So what we are doing here now is that we are assuming that we do not have the original domain of both images, in our case, visible and thermal. So we are thinking, if we have RGB image, what would happen if we generate a synthetic thermal image and then fuse them, and then to see how our object detection model would perform. So the motivation of this research is that first, we want to see if we use different features of each modalities, in our case, RGB and thermal. How is it going to affect the performance of object detection models? And another thing is that we did a thorough literature review on thermal object detection, and we saw that each researcher presented an algorithm, and then they trained and tested the models on a custom self-collected data set. So we could not have a benchmark. We could not compare the performance of these algorithms to one another. So these are the motivations that led us to this research. So what we did, we picked a publicly available data set which contains thermal and RGB images, but they are not paired. And then we train and test the models on the original domains to see how the models would perform on these original domains. And then we created synthetic data, and then we fused this data, and then again we tested these object detection algorithms. So the algorithms that we used are YOLO V7 and FastRCNN. Can we go to the next slide, please? So as you can see here, we have the performance comparison of FastRCNN and YOLO V7. And as you can see, we did a sensitivity analysis based on the weather and hours. So we have clear weather and partly cloudy weather. And for each weather, we have daytime images and nighttime images. And the metric that you see here is MAP 0.5, which is the mean average precision for detecting objects in the images. Based on the results that we have so far, we see that for the FLIR data set, FastRCNN is working better than YOLO V7 overall. And another thing, we used CycleGAN for producing the results, generating the synthetic data. And we can see here that using CycleGAN as is cannot perform, actually cannot develop the performance of object detection algorithms. And only using the original domains of the data set have the best results. Another thing that you can see here in the graph is a very big gap between the performance of each of these object detection algorithms in the daytime and the nighttime. You can see, for example, for clear day images, we have 0.5, but for nighttime images, we have 0.1. And that's a really big difference. So more sensitivity analysis is ready on my poster. So if you have any other questions, I can see you at the poster. Thank you.
Thank you. Thank you so much, Mehrsa. Next, we have Stephen Steinle, who is a PhD student at USF's Advancing Machine and Human Reasoning Lab. He's a 7-year veteran of the United States Navy who has worked with both cyber intelligence and cybersecurity. His research focuses on identifying and modeling cognitive traits of individuals with large language models. Stephen?
Good afternoon, everyone. My name is Stephen Steinle. As was just mentioned, I'm a PhD student at the University of South Florida, Department of Computer Science and Engineering. Today, I would like to discuss with you how we can augment multi-factor authentication with cognitive modeling. Let me define some terms first. Multi-factor authentication is a contemporary security strategy where a user is challenged and is required to present multiple credentials in order to be authenticated. These credentials often take the form of, also, next slide, please. Skip the slide. Yes. These credentials often take the form of something you know, such as a password, something you have, such as an access token, and something you are, such as a biometric. Next slide, please. Cognitive modeling is the process of making a computer behave more like a person. One of the most effective ways to do this is to utilize the cognitive traits of a human. Cognitive traits are simply the behaviors and characteristics that determine how we act. Let's look at an example here. Imagine that you're ordering food at a fast food restaurant for your coworkers over the phone. If they present you with a large list of items, you're much more likely to lose things than if they present you with a small list of items. This is an example of working memory. Cognitive traits, next slide, please. Cognitive traits each act as an individual puzzle piece when forming your comprehensive neural profile. We can utilize this in authentication by determining which subsets of cognitive traits are most individually unique to you. One of the best methods to do this is through the use of cognitive tasks. This is because cognitive traits cannot be observed directly and must only be observed through the metrics that we can see after performing the task. Next, please. One of the best tasks for this is the semantic fluency task. During the semantic fluency task, an examiner will provide the user with a category word, such as animals. The user will then be required to provide the examiner with a number of items that belong to that category word. For example, dog, cat, mouse, etc. Next slide, please. In order to use this for multi-factor authentication, we must first gather the cognitive traits that belong to the individual. We can do this by providing them with a battery of examinations, such as the semantic fluency task. Next, please. Once we collect these cognitive traits, we can map them and determine which of the cognitive traits are most individualizing, because it is absolutely possible for multiple people to provide the same semantic fluency lists. Once we have these cognitive traits, next please, we can then query the user upon authentication, upon login. This will allow us to authenticate the user by comparing their new results with the results provided during their initial battery. Notice that during this entire process, we haven't had to use passwords, credentials, or even biometrics. This means that while an adversary may be able to steal any number of these things through hacking, or even simple theft, it will be much more difficult for them to completely steal somebody's cognitive profile. If you have more questions, I will be happy to talk with you more at my poster. Thank you for your time.